mathematics. This is a part of integration, but we are just going to take a small part because we cannot look at the whole topic, and that is integration of partial fractions. Integration of partial fractions. One wise man exclaimed somewhere and said that he will not concern himself with matters which are too great for him, neither will he exercise himself in issues which are too high for him. Over time, as I've been teaching, I've realized that this is almost the attitude of most of A-level students towards mathematics. But we want to demystify that. I want to assure you there are no issues which are too high in mathematics. There are no matters which are too great in mathematics. What can make issues too great or matters too great for you is when you lack the prerequisite information, So in this case here, there are certain prerequisites you're going to need, or there are some things I'm going to presuppose that you already know. For example, I expect you to be having, say, an idea in some basic algebra. That is, you know something about the polynomial remainder theorem. You know how to factorize polynomials and all that kind of thing. Then I will also presuppose that you have an idea on differential calculus, or what you called differentiation. By senior 6, that is supposed to be covered. And basically, I'll also expect you to have some information on basic integration. That is, the starting bits of integration. You know how to integrate a polynomial. You know how to apply some techniques like changing the variable, and then techniques like trigonometric substitution. So I'll expect you to be having an idea on that. For our friends, those who are in senior 5, you may feel like you want to move away. There are some things you're going to pick. For example, here we are going to be looking at decomposition. You're going to be looking at decomposition. One time a question was set, and it required using the binomial theorem to expand a quotient of polynomials using the binomial theorem. And the quotient was so complicated, and if someone had an idea on decomposition into partial fractions, the question would be very, very simple. And binomial theorem, this is a topic by now you should be covering if you're in senior 5. We hope you're doing a lot of personal revision. So this is going to benefit a lot the candidates, those who are preparing for, who are optimistic that despite the global disruption we have, you're still working hard, hoping that you're going to sit for your UNEB exams by December. So, talking of prerequisites, we shall look at the first things first. What a weird heading. Here, we just want to get some few definitions to set the language we are going to use so that we may be able to communicate. First of all, we shall let f of x and g of x to be polynomials. Then this guy here, this quotient of polynomials, is called a rational function. It's called a rational function. So every time you hear me talking about a rational function, what should come in mind is that I am actually talking about a function which is expressed as a quotient of polynomials. Now, there are some other terminology we shall be using. For example, this is a quotient, it's a fraction. If the degree of f of x is less than the degree of g of x, then this rational function here is said to be a proper fraction. Said to be a proper fraction. So every time I'll be talking about a rational function being proper, all I'm meaning is that the degree of the polynomial f of x is less than the degree of the polynomial g of x. Otherwise, this guy here is said to be improper. Is said to be improper. So the moment f of x and g of x have the same degree, or g of x has a smaller degree compared to f of x, then that fraction is said to be improper. Now, some other terminology you'll hear being used a lot is about factors of that denominator there, g of x. So we let f of x over g of x be a rational function. In other words, f of x is a polynomial and g of x is also what? Is also a polynomial. If m is the greatest, if m is the greatest positive integer for which ax plus b to the power m is a factor of this guy here, g of x, the denominator, then ax plus b is said to be a linear denominator of multiplicity m. If m is the greatest positive integer for which this guy here is a factor of g of x, then this guy alone, without the power, is said to be a linear denominator. This is a linear function. A linear function is basically a polynomial of degree 1. So the moment there is such a factor in the denominator, there is such a factor of g of x, then we say it's a linear factor of multiplicity m. We shall pick a few examples to understand most of these things. B, let ax squared plus bx plus c be irreducible. That is, it cannot be factorized. In other words, you cannot decompose it to a product of linear factors. And m be the greatest positive integer for which ax squared plus bx plus c to the power m is a factor of g of x, then ax squared plus bx plus c is said to be a quadratic denominator. A quadratic denominator of multiplicity m. So the multiplicity is simply the number of times you're multiplying something by itself. A quadratic expression, that's just a polynomial of degree 2. Now, the key words here is we want ax squared to be irreducible. If he is not irreducible, in the term of partial fractions, we will not refer to him as a quadratic denominator. So, for example, in the function say x squared x minus 1 over x into x plus 1 into x squared plus 1. In that expression there, we could introduce some powers so that we may bring out the concept of multiplicity. This is what we are taking as our f of x. And this polynomial down here is what we are taking as our g of x. Of course, when you open up those brackets, you're going to end up with a polynomial because the product of polynomials will always give a polynomial. Now, this is a linear factor. It's a linear factor, and it has multiplicity 1. That is, it's a linear factor. In other words, it's in the form ax plus b. And in that case, a is 1 and b is 0. Then this factor here, that is the x plus 1, is also a linear factor, but it has multiplicity 2. That is, 2 is the greatest positive integer for which x plus 1 to the power m is a factor of the denominator. Now, when you look at this guy here, that is x squared plus 1, we cannot reduce this polynomial here into a product of linear factors with the rational coefficients. And so we take him to be a quadratic denominator. But 3 is the highest power for which this guy is a factor of g of x. So this is a quadratic factor, but has multiplicity 3. So I hope that concept has sunk deep. And sometimes when the multiplicity of a factor is greater than 1, we normally use the words a repeated factor or a repeated linear factor or a repeated quadratic factor. So when those words come up, there is no reason to get confused. Now, those are basically the things which are going to be appearing in the language that is going to be used. Why? What are partial fractions? Because we are saying we want to integrate partial fractions. What are partial fractions? I want you to recall from your O-level, in algebra, you would get, for example, a question, and they would tell you to simplify 1 over x maybe plus 1 over x plus 1. And so what you would do, you would first of all get the LCM, and then you get this, divide by this, which is just x plus 1. You multiply by that, and then you get this, divide by this, which is x, times 1, which is just plus x. So that you would end up with something like 2x plus 1 over, of course, this is x squared plus x, and then x squared plus x. So here, what you were doing, they were telling you to simplify, and that is what you did. In other words, you were compressing, you were writing a compressed form. However, here, when you're decomposing in partial fractions, we will be moving from this direction back to that direction. In other words, we get something in compressed form, and then we break it, and we shall be calling that decomposing. So these two guys here are the ones we are calling the partial fractions. Partial fractions of that guy there, 2x plus 1 over x squared plus x. So in other words, this object here, the whole of it, that sum there, we could give it another name and call it the decomposition of that guy there, 2x plus 1 over x squared plus x, the decomposition into partial fractions. Now, why do we bother with decomposing into partial fractions? Why decompose? Most of the things which mathematicians do in life, they're intended to soften or to simplify life. For example, here, we are talking about integration. Now, you will note that this guy here, for example, the integral of 2x plus 1 over x into x plus 1 dx, is not very obvious. It's not very obvious. Those who have been doing a lot of practice in integration, by now you know that there are some integrals you can just look at and then you know the answer. But this is not one of them because it is still in a form which is a little complicated. Until you break it down. You break it down to the form integral of dx over x and then plus integral of dx over x plus 1. So at this stage now, life looks easy. You can even just throw the word. You can even just throw the answer. So that is what partial decomposition does. Now, the most important thing is to know how do we decompose into partial fractions. Now that we know the relevance of what we are doing, how do we decompose? When we are going to decompose into partial fractions, there are things we have to consider. Let f of x over g of x be a rational function. And this is the function which we want to decompose. When you're decomposing this function, there are two things you have to consider. You have to look at the type of fraction. Remember now we have two. that is, we say the improper fraction, where the degree of the numerator is greater or equal to the degree of the denominator. And then we have the proper fraction, where the degree of the numerator, f of x, is strictly less than the degree of the denominator. So you have to consider the type of fraction, and that's why we began by talking about the type of fraction. And then the other thing you have to consider is the type of denominator. And we have also talked about the type of denominators we should expect at this level. That is the linear denominator of a given multiplicity, and then the quadratic denominator of a given multiplicity. So the type of fraction is what you consider first. We have to first of all look at the type of fraction. Now, if this guy here is improper, if this guy is not proper, you use long division. We all know the long division algorithm from our remainder theorem. So you use polynomial long division to express it in the form that is a some polynomial plus a proper fraction. Some polynomial plus a proper fraction. You apply polynomial long division to express this guy in that form. And if you're well conversant with your remainder theorem, then you are sure to note that that polynomial there is the quotient when f of x is divided by g of x. And this proper fraction is of the form the remainder of the denominator g of x. Now, after expressing it in that form, then you proceed to decompose the proper fraction, this guy here, as follows. So basically, we apply the decomposition algorithm on a proper fraction. So the moment you look at the rational function, first categorize the type of fraction. Is it proper or improper? If it is improper, first break it down into that form so that you focus on the proper fraction. Now, if it is proper, how do we decompose that? And that is what we are going to look at this moment. So B, if f of x over g of x is proper, then we consider the type of denominator. We consider the type of the factors of the denominator. And it is those factors which are going to give us the general idea, the general view of how the decomposed form of the fraction is going to look like. And this is the algorithm. For each linear denominator, of multiplicity m, we could have an idea of what the denominator is. For each linear denominator, ax plus b of multiplicity m, we have already defined all this terminology. There exists partial fractions of the form in other words, when you go to g of x and you look at the type of denominator, and you find that there is a linear denominator and it has
buli ku BBS telefayina yaffe ey'obwakabaka bwa Buganda. Twakutegeezezza tujja kuba tukutwala butereevu ate okulaba minisita ng'ayogerako eri eggwanga ku nsonga ezigenda maaso. Ku ssaawa eno butereevu ke tufune okwogera kwabwe.
So this is information for yesterday, as of yesterday, 26, and we are releasing it now. We'll be releasing the information of today later.
Okay.
So the Ministry of Health wants to confirm 4 new cases of COVID-19 in Uganda. This brings the total number of cases to 18. You recall we had 14 cases. So we bring new confirmed cases today, 4. That makes the total 18.
Sure.
I'm sure people have been counting, and everybody knows we've been having 14. So with the addition of 4, we bring it to 18. Let me just give a little detail